Hello and welcome back. Let's check 8.6 out, DeMoivre's theorem. This is really kind of pretty cool, I have to say. I like DeMoivre's theorem. DeMoivre's theorem lets us raise complex numbers to any power, any positive integer power, very quickly without actually having to multiply the whole thing out. So if we take a complex number, a plus bi, and we write it in its equivalent trigonometric form, then we can take z to any power, which is equivalent to a plus bi to that power. And by repeated use of that multiplication template that we saw in the previous section 8.5, we just take the modulus of z and raise it to the power p. And the cosine, well, the new argument of z to the power is just p times the argument of z. So the new argument is p times the original argument plus I sine p times the original argument. So pretty neat little template. Let's use this to find 3 plus I to the 9th power. Well, here I drew z already for us. So z falls in the first quadrant. We go over the square root of 3 up 1, so you can recognize this as a 1, 2 square root of 3. So this must have a length 2. So it's going to be 2 cosine. Well, the argument here, we went up 1, so the short side is parallel to the y-axis. So we went up 1, so that angle must be 30 degrees. Cosine of 30 degrees plus I sine of 30 degrees. So according to this little template in DeMoivre's theorem, z to the power p would be, oops, let's erase that and let's call it z to the power 9 because we are looking specifically at 9. Okay, so I'm just going to change that p to a 9. Z to the power 9 is just going to be the original modulus to the power 9 times the cosine. Well, 30 times 9 is 270 degrees. Plus I sine of 270 degrees. All right, now we can keep going with this. 2 to the 9th is 512, assuming that I calculated that correctly. Just make sure. 512. The cosine of 270 degrees, well, 270 degrees is coterminal with the negative y-axis. So this is going to be, the cosine is going to be 0, and the sine is going to be negative 1. So square root of 3 plus I to the 9th power is just negative 512I. Isn't that kind of cool? So we didn't have to do square root of 3 plus I times square root of 3 plus I times square root of 3 plus I 9 times. All right, so it saves us a lot of effort. All right, the nth root theorem can also be derived from our previous section. Again, check your book for the proof of that. If anybody wants to go over it, I'll be more than happy. The nth root theorem says, if we have a complex number, a plus bi, and n is any positive integer, then the n distinct roots, so that means if there's the 5th root, then we can find n roots of z, can be found by, ready, bear with me, the nth root of z is going to be the nth root of the modulus times the cosine. Now your new argument is going to be your original argument divided by n, but we're going to have, whatever n is, we're going to have that many roots. So we're going to keep adding fractions of 360 until we exhaust one trip around the plane. So again, just bear with me. So the new arguments, because we're going to have as many zeros or roots as however large n is. So it's going to be your original argument divided by n plus 360k divided by n. And k is going to start at 0. And it's going to go all the way to 1 less than the value of n. All right, so again, bear with me. Let's find all complex square roots of z equals negative 4 plus 4 square root of 3i. So we are looking for the square roots of z, which are negative 4 plus 4 square roots of 3i. Ugh. All right, we want to get better, more precise values. All right, So let's do this. So complex square root. So n is 2, right? Because we don't see it here, but n is equal to 2. All right, so let's put in trig form. Z is equal to, well, let me draw this guy. -4 plus 4. So here's -4. This is 4 square root of 3. That would be the number right there. All right, so this one's going to take a little more work. So we're going to find R. R is going to be the square root of -16. Whoops, nope, -4 squared, which is going to be 16. I'm just thinking ahead. -4 squared plus 4 square root of 3 squared. So 16 plus 16 times 3, right? So that's going to be 64. Square root of 64, which is 8. So R is 8. And then what is this angle right here? I'm going to call this one alpha. Let's say I'm going to do the sine of alpha is equal to 4 square root of 3 over 8. Right, so 4 square root of 3 over 8 is square root of 3 over 2. So alpha is 60 degrees. So I know my reference angle is 60 degrees, so therefore our argument must be 120 degrees. So Z is equal to 8, excuse me, cosine of 120 degrees plus I sine of 120 degrees. So according to this template, to find the two square roots, the square root of Z is going to be the square root of 8 times the cosine of 120 degrees divided by 2 plus I sine of 120 degrees divided by 2. Oh, I lost that in there. Hold on. Take that back. I lost a piece in there. My two square roots are going to be, sorry, I lost that part. We don't want to lose that part. So my two square roots are going to be, ready? I gotta slow down. Z is equal to, it's going to be the square root of 8, the square root of modulus, the cosine of 120 degrees divided by 2 plus 360k divided by 2 plus I sine the original argument over 2 plus 360k over 2, for k just equals 0 and 1. Starts at 0 and it ends 1 less than the roots we're looking for. So let's just clean this up a little bit. I'm going to call this the square root of 8, the cosine of 60 degrees plus 180k plus I sine of 60 degrees plus 180k. So now let's find it for, let's do k equals 0. We'll get our first square root. So if k equals 0, we get the square root of 8 times the cosine of 60 degrees plus I sine of 60 degrees. And these are nice angles, so we're going to work these guys out. It's going to be the square root of 8 times the cosine of 60 degrees, which is 1/2, plus square root of 3, I square root of 3 over 2. All right, now we're going to distribute this. We have, I'm going to change the square root of 8 to 2 over the 2 square root of 2. So we have 2 square root of 2 over 2 because the square root of 8 is 2 square root of 2. Plus 2 square root of 2 times I square root of 3 all over 2. Simplify, square root of 2 plus I square root of 6. So this is our first square root. All right, let's find the second square root of z. This time we're going to let k be 1. So if k equals 1, we're going to get the square root of 8 times the cosine of 60 plus 180 plus I sine of 60 plus 180 degrees, which is 2 square root of 2. I'll do that right now. Cosine of 240 degrees plus I sine 240 degrees. So 240 degrees has reference angle 60 degrees. So 2 square root of 2, and 240 degrees is in quadrant 3. So it's going to be negative 1/2 plus I times negative square root of 3 over 2. Let's clean that up. Let's just distribute. It's going to be negative square root of 2 when I multiply those two together, plus I, 2's cancel out. So it's going to be negative square root of 6. So negative square root of 2 minus I square root of 6. Huh. So therefore, the 2 square roots of z equals negative 4 plus 4 square root of 3i are the square root of 2 plus I square root of 6 and negative square root of 2 minus I square root of 6. Oh, that was a lot of work. That's only 2 roots. What if I wanted to find the 6th roots? So if these are the square roots, if we square both of these, you should get that number right there. So to do, show the square root of 2 plus I square root of 6 squared is equal to negative 4 plus 4 square root of 3i, and negative square root of 2 minus I square root of 6 squared equals negative 4 plus 4 square root of 3i. See if you can do that. Check it. Convince yourself that these templates work. All right, what if we were asked to find the 6th roots? Just going to show you the process. We're not going to find the exact value of each. We tend to only find the exact value if the angles are one of our multiples of 30 or 45. But the 6th roots, let's first put this number in its equivalent trigonometric form. I'm going to go over square root of 3, up 1. Right, so here's my point right there. You can see my angle must be, that's a 1, 2 square root of 3, so R is 2. My argument is 30 degrees. The better you know your trig and your basic triangles, the easier that this is. So Z is equal to 2 cosine of 30 degrees plus I sine of 30 degrees. 6 and is 6. So the 6th roots, ready? The 6th roots of z are going to be the 6th root of 2, which is not a nice number. We would just leave it like that, times the cosine of 30 degrees divided by 6. I did it again. At least I caught it before I went too far this time, right? Plus 360k divided by 6 plus I, and then that whole argument is that same mess, 30 divided by 6 plus 360, k divided by 6. So let's clean this up. This is going to be, can I get it all on one line? It's going to be the 6th root of 2 times a cosine of 5 degrees plus 60k plus I sine of 5 degrees plus 60. Okay, 60 comes from 360 divided by 6. So we're going to start at 5 degrees. We're going to keep adding multiples of 60 till we're back coterminal with 5 degrees. So when k equals 0, we get our first root. It's going to be the 6th root of the square root of 2. K is 0. Both those terms wipe away. It's going to be the cosine of 5 degrees plus I sine of 5 degrees. And again, 5 degrees is not a nice angle, so we're going to leave it at that. K equals 1. Well, now we're going to add 60 degrees to 5. The second root is going to be the 6th root of 2. The cosine of 65 degrees plus I sine of 65 degrees. K equals 2. 6th root of 2. We're going to add another 60 degrees. Cosine of 125 degrees plus I sine of 125 degrees. K equals 3. We're going to stop at k equals 5. And then we stop one less than what the value of the root is because we start at 0. So it's going to give us the 6th root of 2. Add another 65 degrees, 185 degrees, plus I sine of 185 degrees. At 4, we're going to have the 6th root of 2. Add another 60 degrees. We're going to be at 245 degrees. So what's nice about this is we can find the exact roots by leaving them in their trig form. The last root would be at 60 degrees. We are at the cosine of 305 degrees plus I sine of 305 degrees. Now notice if we added 60 again, would be at 365, which is coterminal with 5. So those would be the values of your 6 roots. All right, have fun with that. See you in the next chapter.